Hello, AP Chemistry students. This is Mr. Chan, and today is August 24th. What this will be is a series of short and brief videos that will cover topics that we didn't have a chance to cover back when last year in the COVID-19 pandemic. So what I'm going to do is I'm going to be talking, this will be the first of maybe about 3 to 4 videos that will cover topics that we should have covered in grade 11 that we were not able to do so. So the onus will be on you to sort of go through this on your own, and hopefully you are able to understand the material. And if you have any questions, the onus will be on you, again, is to ask me. All right? So what I'm going to be doing is I'm going to be sharing my screen. So let's see, share screen, and let's do the OneNote. Okay. Now, one of the things that I wanted to talk to you folks about is something called the valence bond theory. Now, when we look back to bonding, now, regardless if you were in Chemistry 11 or Chemistry 11 honors, when we went into bonding, recall when we talked about bonding, it was talking about the sharing of electrons between two atoms, okay? And remember, depending on the pole, like where the two electrons were that were shared, it would determine whether it was non-polar covalent, covalent bond, or ionic. All right, so that was where we had left off in terms of bonding, okay? So the two conditions need to be met for bondings. The orbitals from two atoms must overlap, and the total number of electrons in both orbitals is no more than 2. So you're sharing electrons. Now, since the strength of a bond depends on orbital overlap, orbitals bond in directions in which they point to get maximum overlap. Now, notice I'm using arrows to represent electrons, and notice the arrows are in opposite directions. Now, why are they in opposite directions? Is because they want to minimize the repulsion between the electrons. So it goes back to the idea of a magnet. You know, north and south attract, okay, and you minimize repulsion. Now, where you have seen this before is probably when we were doing atomic theory, and for those of you that did orbital diagrams, let me see, remember when you did like the SPDF and trying to figure out, let's see, we're here, you know, the electron configurations. Remember when we did the electron configurations, when we were drawing the electrons as arrows, they were in opposite directions, okay, to minimize the repulsion. So that is still prevalent. Now, when we look at the orbital diagram for carbon, it looks like this. It's 1s2, 2s2, 2p4. Now, it looks like it only has two unpaired electrons to share. So how are we able to get CH4 where there are 4 electrons for sharing? So notice here, there's only 2 electrons. So we go WTF. So how can you have 2 electrons that are by themselves? And if we need electrons to overlap to form a bond, how can we have 2 electrons that are unbonded form 4 pairs? So there seems to be a disconnect between here. Okay, so the idea came up with is the idea of something called hybridization. So in this case, for CH4, one needs to assume that during bondings, electrons are excited and the s and p orbitals merge together to form 4 orbitals that are identical to each other. Okay? This merging of orbitals is called hybridization. So in this case, we have our atomic orbitals. This was the one that you would draw when we were trying to figure out the electron configurations. Now, in bonding, what happens is the orbitals merged, and this is called the hybridized orbitals. Now, so what happens is this, the hybridized orbitals, why do they theorize this, is now these two pairs, these two electrons are now broken up. And what happens is that it allows us to have the 4 single electrons available for bonding. Okay. Oh, did my pen run out of ink again? Okay. Okay. Now, whoopsie, looks like my pen is not working again. Now, so that is the idea of hybridization. Now, the one thing you need to realize is this. The number of orbitals, when we talk about orbitals here, these are hybridized. So the number of hybridized orbitals is equal to the total number of atomic orbitals that are combined. Okay? So, for example, here we have the S and all of the 3 P's joined together. So 1, 2, 3, 4. And this is why it's called the sp3 hybridized orbitals, because you took the s and the 3 p orbitals from the atomic orbitals and joined them together. Now, the types of hybridization and corresponding shape. So depending on the hybridization, what happens is that it corresponds to the shape of the molecule. So when you have an sp2 hybridization or sp hybridization, that's a linear shape. So how do we get the sp? Because you have an s and a p, so you have 1, 2. So this is called the sp hybridized. Now, how does that look? It looks something like this. So I'm going to open this up. Okay, I'm going to stop sharing, and I'm going to share my screen. I'm going to share you this one here. So what you can do is here, so the blue is the S, the P is in the yellow. When they talk about hybridization, notice it turns to red. So that is the SP hybridization. So notice the central blue is gone and it's merged together into this SP. Okay? Now, so that's where we get the linear model. Okay, let me just move this away. Now, for sp3, it is trigonal planar. Okay, so what you have is you have the sp3. So they took the s orbital here, oh sorry, sp2, and you took 2 of these here. So you have 1, 2, 3. This is called sp2 hybrid or hybridized. So this would give you a trigonal planar shape. Again, how would that look? Okay, if I said stop share, share again, okay, we have this one here, okay? So when you start, we have the S and the P's. Notice SP2, okay? And what you have is you have a triangular pattern, okay? A trigonal planar pattern, okay? Triangular, and it's in the single plane, all right? Let me just close some of these off. So close window, okay, share screen. So right now you have a corresponding hybridization along with the corresponding shape. So if we keep on going down, oopsie, come on, there we go. So we have sp3, it's tetrahedral, okay? So that's like CH4. So you take the S and the 1, 2, 3, you get sp3 hybridization. So what you have is you have here 4 electrons for bonding. And that's why it's tetrahedral, okay? Now, for those of you that don't recall doing the shapes or this type of, tetrahedral, or if this sounds new, please make sure you go back to the other videos that I have to sort of review, refresh your memory, okay? Now, for the sp3, remember we talked about for Lewis dot structures, you had expanded octets. And I talked about the fact that the reason for expanded octets is because of the fact that you have the d orbitals for the electrons to go into, okay? And so this is where it comes in. So let's say for phosphorus, why is phosphorus able to have more than 8 electrons in the outermost shell? Okay, so in this case, you have the atomic orbitals for PCl5, and this is, we could say, electron configuration. And so what happens is this. When it is bonding, the pair of electrons that are here get split up, and what you get is you get 5 electrons ready for bonding, okay? So you have 5 electrons for bonding, okay? Now I put up here sp3d1, and you notice here it says sp3d, okay? It doesn't matter. You could put just d1 or d, both are the same. And again, for the octahedral, what happens is you have for sulfur, here you have regular sulfur, okay? The atomic electron configuration for sulfur, which is, all right? Well, it's not sulfur. This should be 3, sorry. Oh, my pen didn't work, okay? So my pen's out of ink again. And so what you get is sp3d2 is octahedral, okay? So what happens is, for this particular lesson, you should be able to understand the hybridization corresponds to the number, to the shape, okay? And to the number of electrons that are available for bonding. Now, one thing one vocabulary term that some of you might have seen, okay? This regular electron configuration could say we are ground, That's the ground state. Okay? Is because it is not doing anything, it's not whatever. Okay? When it's hybridized or anything that's different from the regular electron configuration, we call this excited. Excited state. Okay? All right? Okay. So that is what I wanted to talk about, is one of these mini lessons that I was not able to finish last year. So I wanted to talk about this this year. So again, what is this hybridization? Is basically taking the atomic orbitals and breaking them apart, combining them so that you have electrons that are not paired up that are available for bonding. All right, folks? All right. Thank you very much. The next lesson that I will have will be on something called sigma and pi bonds. And then what I will do is I will go over an example that combines today's lesson and the next lesson for you folks. All right, folks. Thank you. Have a good day.